Rubies and sapphires have been the objects of desire for mankind throughout history. These fine gems take their place, along with emeralds, as the top 3 most valuable colored gemstones in the world. My name is Palke. I'm a geologist and I work primarily on gemstones. The focus of this lecture will be on the mineralogy of these highly sought-after gems. To a geologist, rubies and sapphires are more accurately referred to by their accepted mineral name, corundum. A mineral is simply a solid material that satisfies 3 criteria. First, a mineral has to have a regular, repeating crystalline structure. This means the atoms in the mineral have to be put together in a rigid and symmetrical pattern. Secondly, a mineral has to have a definite chemical formula. And finally, a mineral has to be naturally occurring. Let's consider more carefully that first requirement that says a mineral has to have a crystalline structure. Here is the crystalline structure of the mineral corundum. This is what all rubies and sapphires look like at the atomic level. In this diagram, the light blue balls represent atoms of oxygen, and the red balls represent atoms of aluminum. This brings us to the second requirement, which is that all minerals must have a well-defined chemical formula. For corundum, this is written out as Al2O3. Without getting bogged down too much in chemistry, this simply means that all corundum crystals and all rubies and sapphires are composed almost only of atoms of aluminum and oxygen in a 2:3 ratio. You remember the final requirement is that minerals must be naturally occurring. This means that although rubies and sapphires can be made in a laboratory setting, these materials should not be considered to be minerals, but should be called synthetic ruby or synthetic sapphire. This is true even though at an atomic level the synthetic versions look exactly identical to natural rubies and sapphires. In fact, synthetic rubies and sapphires can actually make quite attractive gems in their own right. An example of a synthetic pool of corundum is shown here with a natural sapphire for comparison. Let's talk a bit more about the crystallography of corundum. Here is another view of the corundum crystal structure, looking at it from a different angle than our previous example. Now, the structure looks pretty complicated, but if we pay attention, we can start to make some sense of it. Note that the way we have represented the structure here, it looks like a hexagon. Corundum actually belongs to what we call the trigonal crystal system, which means it has threefold symmetry like a triangle. However, because of the way the crystal structure is expressed, corundum crystals often have a hexagonal shape. And here's a great example of this. This corundum crystal has a striking hexagonal cross-section when viewed down the same direction in which we're viewing the atomic structure here. It turns out that the shape of a crystal is a great way to identify which mineral it is. The crystal faces we see in well-formed minerals are, in fact, directly controlled by the internal atomic structure of the mineral. Each of the different faces is actually a plane that slices through this structure in different orientations. And depending on the growth environment in which the crystal grew, different crystal faces will be favored in different situations. A common form for corundum is a tabular hexagon, as seen in this example. Corundum crystals can often have this hexagonal form stretched out into long, slender prisms, as we see here. In some cases, the corundum forms pyramidal structures, as in these dogtooth crystals. There are several aspects of this crystal structure that make ruby and sapphire so appealing as gemstones. First, the aluminum and oxygen atoms are held together very tightly in this structure, which makes rubies and sapphires extremely hard. Now, why is that important? Well, a high hardness means rubies and sapphires can keep their polish very well for a very long time without getting scratched by other materials. Secondly, the aluminum and oxygen atoms do not absorb light on their own, which means corundum can be very transparent. And transparency, of course, is what makes a gemstone beautiful. Finally, the aluminum and oxygen atoms are held together very closely, making rubies and sapphires very dense. This doesn't necessarily make them good gemstones, but it does mean they don't get swept away when the original rocks that hosted them get washed away during geological weathering. This allows rubies and sapphires to accumulate in what we call alluvial deposits, and this makes it relatively easy for miners to extract them. We'll discuss this more in the next lecture. Let's get back to chemistry before we wrap things up. Remember earlier we said that corundum is made up of only atoms of aluminum and oxygen in a 2:3 ratio. Now, the truth of the matter is that most natural corundum is typically composed of more than 99% oxygen and aluminum, but there are usually other traces of elements present as well. These impurities are actually a good thing for the most part, as these other elements are where all the color comes from for our rubies and sapphires. For example, the red color of rubies is caused by the presence of chromium substituting for aluminum in the crystal structure. Now, blue sapphires owe their hues to the simultaneous substitution of both iron and titanium in the structure. Yellow sapphires are often caused by the presence of iron without the involvement of titanium. And green, of course, is going to be the result of the mixture of blue and yellow components. There are other causes of color in corundum, such as missing electrons on oxygen atoms, which causes a yellowish-orange color, and vanadium, which can cause a green-blue color. Here's an example of how this works. What we're looking at here is the optical absorption spectrum for chromium in corundum. The high points in the curve are where the chromium atoms absorb a lot of light, and the low parts are where most of the light gets to travel through the ruby without being absorbed. Overlaid on this are the colors corresponding to the different wavelengths of visible light, from blue light at around 400 nanometers up to red light at around 700 nanometers. What we see is that chromium in corundum strongly absorbs most of the blue and green light, but lets almost all of the red light through. In this case, the light returned to our eyes is red. So the red color in rubies is caused by the selective absorption of certain wavelengths of light and selective transmission of other wavelengths. To see other examples of this, the link shown here will bring you to the website of Professor George Rossman from Caltech, and his site has much more detailed information about the causes of color in corundum and other minerals, if you're interested. This, in essence, is the foundation of everything we know about the legendary gems ruby and sapphire. It's almost unbelievable that nature can produce some of the most valuable gemstones from only two atoms, aluminum and oxygen. If you join us for the next lecture in this series, we'll go into more detail about the geological conditions of ruby and sapphire formation, and we'll discuss exactly how nature pulls off this tremendous feat.